So Ida Arent Kirknel has a bachelor degree in chemical engineering and a master in petroleum engineering, both from Technical University of Denmark, DTU. Ida's main technical focus has been always on thermodynamics, modeling, and how it can be used to improve the current state of technology. As a research assistant at DTU, she has been involved in multiple projects in the oil and gas industry as well as the geothermal industry. These projects have all been focused on scaling and corrosion prediction by thermodynamic modeling. Currently, Ida is employed at WellPerform as a project engineer. In this position, she is responsible for the thermodynamics modeling and scaling and corrosion prediction. Ida's presentation title is Modeling of Scale and Corrosion Potential in Geothermal Well Plants and Oil Producers. With that said, I would like to let Ida to start her presentation, please. Ida, stage is yours.
Yes, well, thank you very much, and welcome to this presentation on modeling of scale and corrosion potential in geothermal wells, plants, and of course oil producers as well. Just gonna go right to it. So this is a quick outline of the presentation, just so you know what's gonna go on. I'm gonna talk briefly about who I am and who we are. WellPerform, just so I assume that no one knows, well, most of you might not have heard of us. So just to give you an idea of who we are, I'm going to be talking about what scale is for those who don't know, and why model this scale precipitation. Why is it important? I'm going to talk about this thermodynamic modeling software that we're going to use, because we're going to look at this from a thermodynamic point of view. Then I'm also going to talk a bit about what we need for inputs to do these predictions, and then I'm going to go into some examples. Two types of way to present these data. It's going to be a historical profile. It's one type, and then the other one is this risk of precipitation for one sample. And there's going to be some examples from oil producers, and there's going to be some examples from geothermal doublets. So the first part here is who are we and who am I? As Ahmed said, then my name is Ida, and I'm a chemical engineer, petroleum engineer, chemical engineering bachelor from DTU, Technical University of Denmark, and then a petroleum engineering master's, the same place, focused on thermodynamic modeling, prediction, doing both, well, when I took my degrees, and also later doing some research project as a research assistant later at Technical University of Denmark. And now I'm on as a project engineer WellPerform, and I've been there for 2 years, and that's me. So as I said, I'm going to go over this quickly just to give you an idea who we are. We are a partner with Petrolern. Petrolern have been able to do some geomechanics expertise from some of our projects, and we've been able to supply some geology and well engineering knowledge, expertise to some of their projects, assisting them in that. We are based in Denmark, which is Northern Europe. It's in Copenhagen. We also have some offices in Mumbai and in Aberdeen, but Denmark is where we have our main office. And this are a map of some of the projects that we've been involved in. This geomechanics project was where Petrolern was involved, and then we are assisting with a screening project in the US, which will also be one of the talks by one of my colleagues, Tina, who is a geologist, in a week or two. You have the schedule on LinkedIn. And that's what I'm going to say about WellPerform. So back to the technical side of this presentation. And what is scale, and why model the scale prediction? So when we have a producer in the oil industry or a geothermal system or a gas producer, you would always have some kind of water produced, brine, because it's dissolved a lot of salts in it. So, and that, of course, as you know, you also have a water cut, even though you're producing, say, oil. So, as you produce from your well, you have this is, well, let's call it a pure water well, brine well. You have, but of course, it's valid for all the types of wells. So you have some conditions downhole. You have one type of pressure and temperature, and you have a set composition for this brine. Now, as you produce, you have all of these ions going up, but as you go up, you have a change in both the temperature and you have a change in the pressure. So as you move up and have these changes, then the brine at some point will reach a point where it can't keep all of these ions in the solution anymore. And at that point, you would start having some precipitation. For a well located in a chalk field, that will most likely be some calcium carbonate. And that calcium carbonate, it can attach to the sides and then eventually block the well if you don't do anything about it. And all of this is because you have a change in temperature and pressure. So scale is, well, it's salts that builds up in the well, among other things. We will only look at the salts for these examples. They are sensitive to pressure and temperature changes, but as much as you don't want the scale to block your well, it also has a different function, and that is if you have, let's say, just a tiny layer of scale in your well, it would actually protect your well from corrosion. It will act as a form of an inhibitor. So if, I mean, it's not all bad scale, you just need to be able to control it. So it's something that can inhibit corrosion, but it's also block the well. So the reason why we want to be able to model it is that we want to avoid the scale buildup. We want to avoid the reduction of production. We want to be able to optimize our production. And we want to minimize workovers. And then we also want to scan the areas that are exposed to corrosion, because, I mean, if you don't have any scale, then you are exposing the area to corrosion. You have to be aware of that. The software itself that we're using, it's called Extended UNIQUAC. It's a model that is capable of predicting solid-liquid equilibriums in a complex aqueous mixture consisting of electrolytes and non-electrolytes. That means that it can take salts such as sodium chloride and gases such as carbon dioxide, and then it can, if you tell it how much there is of these two different components, then it can tell you the equilibrium, thermodynamic approach. The model is it's a model that has the equilibrium assumptions. So it's a equilibrium tool, so to speak. It determines if you have a given composition of the brine that we talked about before, and you have a different temperature and pressure, then you can apply those inputs and it can tell you which salts are going to precipitate under the given conditions, and also how much, because you're given a certain amount of quantities of ions. The model itself is based on data points. That means that you have made experiments in the real world, and then you are adjusting the model to fit those data. So the parameters that the model uses for this instance, barium sulfates, is based on real world data. In the model is included as an output 185 different salts, just to give you an idea of the scope of the model. Now, for the inputs used in this prediction, we need a number of different things. things. We need the gas composition for this well, especially the CO2 composition, because they have a very large impact normally on a lot of different things. We need the brine composition. We need to know what kind of ions are in the well. We also need a temperature and a pressure profile for the well. You can see an example of that over here. Of course, we only have 2 points here at the bottom and the top, so we assumed a linear change here. We have the temperature that are decreasing as we go up in the well here. And same with the pressure. We have a high pressure at the bottom, and then we have a linear change just because we only have 2 points. Now we also would like to know the gas lift location and composition, and that's because you can have a change in your gas composition as a result of the gas lift. And that can have an impact on your scale potential. Then we also need a well profile for the vertical section, and we need some well history, say acid treatments or milling operations, in order to see what's been done to this as well. As I mentioned, I'm going to look at some examples. We're going to look at 2 different examples, and don't sweat it if you haven't seen these kind of profiles before. I'm going to explain them. So over here on the left, we have this historical type. And on the right here, we have more of a risk-based approach. We're going to start with the historical one, and there is a lot of information to take in and explain. So just be aware that it's going to be a very thorough walkthrough. So you're prepared. The assumptions that we need for this historical output is some assumptions. We need the first assumption that we're using is that we have equilibrium at bottom hole conditions. They are close to reservoir conditions. And I mean, we assume we have equilibrium because you have this brine that have been in contact with the reservoir for a very long time, and thus you also end up with an equilibrium. Then we are, say, splitting the well into smaller sections. So we have a flow here going up through the wells, and then we have different sections. So what we do is, if we have the equilibrium brine here, and then we are sending it to the first section, and then we assume equilibrium for this first section. That means that we have a slightly different temperature for this section than we have for the last one, because we have this continuous change in temperature and pressure. And then we calculate the equilibrium for this section given the temperature and the pressure and other conditions. And then we have the scale remain in this section of precipitation, which means that if we have any scale that precipitates in this section, then it stays in the section and it attaches to the walls, and all of it attaches to the wall. Of course, you can have some that's in the real world that's floating around in the well or doesn't have the time to precipitate. But for this simulation, we are going to assume that it's attaching to the wall. And that's what we're going to do for the next. This arrow here indicates the aqueous composition of the thermodynamic equilibrium. And then that's what we're using in this section. And so on. Now the last assumption that's important to have here is that we have the partial pressure of CO2 as a function of the total pressure. We assume that we have kind of a constant composition of the gas. So if we have 7% of the gas being CO2 at the bottom of the well, then we're also going to have it at the top of the well, those 7%. So of course, the partial pressure of CO2 is also going to change equivalent to the total pressure, because we have high pressure here, maybe 300 bars, and then we move up maybe to 10 or 1 bar. And then of course you have the 7% of the 10 or the 1 and 7% of the 300 bars. Now outputs from these assumptions are the composition of the scale, you know what's going to precipitate, and you know the amount of scale that's going to precipitate. you also get this historical current well profile that we're going to look at now. So I'll split it up into two parts. So just quickly, this is the step out for the well. So you have the top of the well here, TVD, and then step out here, so you can see how the well kind of looks. This down here is assumed to be equilibrium because there's no change in temperature or pressure. So what we have here is historical data. So you would need a lot of data going back from your current situation, and those data can then be used to make these profiles. So this is a period of time that this shows. We have the amount of scale here in inches, and then we have the depth of the well. So we are moving up through the well here. So what we know here is that we have these sections here up through the well. So at the bottom we have equilibrium, there's no precipitation. Then we have the next section, some more precipitation, but it all leaves the precipitation behind. For this case, most of it is calcium carbonate because we have a well from the chalk field. So we have abundant amounts of calcium carbonate in the brine. We have equilibrium at bottom hole conditions. And it all leaves, because we decrease the pressure as we go up in the well, we also decrease the amount of CO2 that is dissolved in the brine. So as we move up, we remove more and more of the CO2, and that has a major impact on the calcium carbonate scaling. So as we move up in the well, we have this scaling profile. And remember, this is 100% of every precipitation for a few months that can precipitate. So this is kind of a worst case. This is without assuming any kind of removal of any type. So what happens here is we have a gas lift located, and for this case we have an increase in the partial pressure of CO2, which also means we have a increase in the amount of CO2 that's dissolved in the brine. So that's why we don't have any calcium carbonate. We do have some barium sulfate, but it's very small quantities compared to calcium carbonate. So you can't see it aesthetically in this figure, because we also want to plot the calcium carbonate, but you have some potential barium sulfate in this section here. Now, as we move up again, we are continuously decreasing the amount of CO2 in the well, and that's what we continue to do up until this point. Now, here, the amount of CO2 in the well or in the brine is the same as down here. Remember, we are still decreasing the pressure and still decreasing the partial pressure of CO2 as a result of that. So the amount of CO2 in the brine, or it reaches the same point up here, and that means that when we then move forward, then we have additional calcium carbonate here at the top of the well. So that's one period. Now, if you do that for a number of other periods, it looks like this. So what you see here is it's a different period over here. It has a different brine composition than the period we saw here. You can think of this as a tree stump with all the rings. So you have the composition of the scale is one type here, and then for the next one, it looks like a shorter period as well, but it also has this different composition, and we know what exactly that composition is. It's mainly calcium carbonate. And then we move on to the next one, and the next one, and the next one. And you can see all of the calcium carbonate is removed in this area. Of course, it doesn't mean that you don't have any scale in your actual well, because you might have that it's not a very fast at precipitating, or it precipitates in the brine so that it gets moved up in the well, and then it attaches here. But thermodynamically, if it all stays, it would all stay here. Now, this figure here doesn't account for events such as acid treatments or milling operations. This is purely what would happen if you just let all of your scale precipitate. What happens here is the middle of the well. It means you're blocking your well. And you're blocking your well because you have all of this calcium carbonate scaling and you're not removing it in this example. What you could do is you could implement some of the events that are going to happen to the well, so that, for example, we might have at this point we said, okay, or at this point say we want to remove our calcium carbonate scaling, and then you would remove these periods here mostly, and then what would happen was, you could imagine happening was that you would have it then you would continue producing, but you might have some acidic environment somewhere in the cavity in this area, and then you would, with the new scaling, you could cover that up, and then you would have something called under deposit corrosion, which is corrosion that is hidden with the scale. So it's there, and it's very hard to detect, but it can weaken the integrity of the well. So that's also something you have to be aware of when you're implementing these different events. You could also say we have so many events or so much acid treatments or other operations that we actually end up removing all of this. So you actually don't have any scale in the well. Then you could instead see that you might have some more general corrosion because you don't have these traps. So it would be a more of a general normal corrosion. Of course, you have to decide. It's a case by case, so you can't just say there's one solution. But of course, I hope you understood this. I know it was a bit complicated for people that haven't seen this kind of figure before. But we're going to move on to the next one, which hopefully is going to be a bit more simple or easy to understand. And that is the risk of precipitation based on one sample. Now, we have some assumptions as well for this one. Some of the same, but not as many. We have, again, equilibrium at bottom hole conditions. And for the same reason as before, we have this brine that's been in contact with a certain reservoir that we assume is saturated. And then we have the partial pressure of CO2 is a function of total pressure. So when you degas, when you decrease the total pressure, you're actually degassing some of the CO2. An output for this kind of modeling is kind of a risk profile for each of the salts. It looks something like this. This is from a chalk field as well, and it's a producer, and it's the same producer as before. You can see the temperature, the pressure here, and I included 4 different salts for this example. So you have the temperature and you have the pressure up here. So you have low pressure and low temperature in this corner here. You have the production conditions, is this black line. Of course, it's similar for all of the plots because it's the same well that we are simulating. So what you can see here, this is the risk of barium sulfate precipitation. And we have this line up here. It says 1. So what we use for evaluating the risk is the saturation index. The saturation index is a way of telling how oversaturated or undersaturated my brine is. If the saturation index for a salt is below 0, then it's undersaturated and that salt won't precipitate. Now, if it's 1, then you won't be able to dissolve any more of that salt in that solution, but it won't precipitate either. Now, if you're above 1, then you could have a theoretical precipitation of the salts. Of course, if it's the more oversaturated it is, the higher the chance you will actually see some saturation. Because again, this model doesn't include kinetics. It's a thermodynamic equilibrium model. So even though at the previous historical profile you saw there was some precipitation, it might not be all of that that's actually precipitating. But back to this one. We have this this one here. This is our saturated brine here. This is this point here is in the bottom of the well. You can see that we assume that it was at equilibrium, so that's why we have this one line here. Now, as we are producing, you can see it's green on the other side, because even though you don't actually have it on the key, but everything below 1 is green. There's no risk, and then everything above 3 is also red. So as we produce for this barium sulfate, for one, you have a decrease in pressure at the beginning primarily, and then you have a decrease in pressure after that. Now what you can see here is that at the bottom you don't really have any risk of precipitation of barium sulfate, but as you're producing you have an increased risk of seeing some barium sulfate in your well. The same is true for the calcium carbonate, which is down here. We have the one line is this one here, just as it was on this one, but it's located differently because it's a different salt. And then as we produce from the well, we are moving to a lower temperature and a lower pressure, and then we are running into saturation index of 2, which we're giving increased chance of precipitation, and then we are ending up in a red area, and this is topside. Now we have the same for iron carbonate, but we don't have where we have the one line here, and then we have, as we produce, an increased risk of this iron carbonate, but we don't have anything at the strontium sulfate, which just tells us that we don't have a saturated brine, and we don't have any risk of seeing strontium sulfate for this well. Now, if we want to do some results, or some what this graph can actually tell, then is that we have, this is the bottom of the well. We have very little risk of scaling. You can see that for all of the 4 salts. But as we start producing at the last section of the well, you actually have an increasing risk of precipitation. You have that both with calcium carbonate, have that for iron carbonate, and you actually also have that for barium sulfate, but not as severe. Now, what you have to be aware of is that if you have this scaling potential at the top, then but you don't have it at the bottom, which means that your bottom could be exposed to different kinds of corrosion. You have to be aware of that. Now, speaking of corrosion, the iron carbonate is often a product of corrosion. So if you see that in your well, say you see that up top, then you should be looking at the further down in your well to see if you have any corrosion. So this is a tool of seeing you have some scaling potential that you have to be aware of because it can block your well, but you also have some areas that doesn't have any type of scale, and that could then be more exposed to corrosion because of this inhibiting factor that the scale can do. The second example that I have of this risk precipitation is of a geothermal doublet. Now, in a geothermal doublet, you want to produce the hot water from the subsurface. You want to extract it, and you want to extract all the heat, and then you want to re-inject it to preserve the pressure in the formation. So we have a very, very simplistic geothermal doublet that we did the simulation on here. We have a producer, we have a top side with a heat exchanger and a degassing unit, and then we have the injector here. Now, these are some of the conditions that we assumed. we have a temperature of 80 degrees. You can see this is low enthalpy. We have a pressure of 264 bars. Well, yeah, you can do the math for the Fahrenheit. And then we have a CO2 content of 7%. As I mentioned earlier, we have the assumption that you don't change gas composition. So we have that at the bottom of the well, and then at the top of the well we have another condition up here, where we say we have a slight decrease in the temperature. We are having a topside run at 10 bars total pressure, and then we have a CO2 partial pressure again of 7% of the total pressure, so 7% of 10 bars. Between these 2 points, we don't have any knowledge, so we assume a linear change in both temperature and pressure. That's what you saw earlier, those 2 graphs. When we go to the top side, we have the heat exchanger and the degasser. So you have a decrease in the temperature to 15 degrees. We have the same total pressure, but we have reduced our CO2. And what we have then for the next point is the end of the injector. So as we inject it, we have a slight increase in the temperature because we have a slightly warmer surrounding than 15 degrees, is the assumption. We end up at the same as the reservoir condition, 264 bars. And as we don't have the same kind of degassing effect in the injector, the amount of CO2 dissolved into the liquid are identical for these 2. Here in the injector. So there's no additional CO2 being added as there was removed in the producer. I have split up the different salts again. The first one is barium sulfate that we're going to look at. So these 3 figures all depict barium sulfates at different stages of the geothermal doublet. Now, the producer here is, again, the assumption was that we have equilibrium in reservoir and bottom hole conditions. So 1 here. So you can see that as you decrease the temperature and decrease the pressure, we go down here, and it's not very severe, but there is a yellowish area over here. So you're slightly increasing the saturation index, and thus also the risk of seeing is as precipitation, but not really severe in the producer. Then that's this point here. So if we look at the top side, the heat exchanger, we are this point here. It's the same as this point here. Again, we are somewhere between the 1 and the 2, and here we have. Again, this is production conditions, but we have this linear expectation. So we have a decrease in temperature, and see here that we have CO2 pressure. That's because our total pressure is constant, but we are degassing a lot of CO2 among others. So as we degas and decrease temperature at the same time, you can see that we are increasing the risk of seeing any barium sulfate. We have the 2 line here, and we continue down into the red area here. And this is then our injection conditions over here. And you can see here that we have a severe risk of seeing any barium sulfate. If we moved to the injector, we start up here with a low temperature and a low pressure. And we assumed a small increase in the temperature and quite a severe or a significant amount of pressure being applied. So we have the production condition going down the injector. We still have a severe amount of risk of barium sulfate scaling here at the top, and then it decreases as we go down. But of course, you can see a lot of scaling top side, but also injector wise. And again, it's not always that, even though the risk of precipitation happening here, you might see it a bit further down, or it might dissolve. So just because it says it's below 2 here, it doesn't mean you don't see it at all. You can attach different sections of the well. But the main areas I would look would be around here. The next salt, it looks like this, and that's strontium sulfate. It's the same kind of figures with the temperature and the pressure, and then the CO2 pressure here. We have the bottom of the producer here, and as we produce, you see the one line is located here on this salt, and we are producing the strontium sulfate, and as we do that, you can see there's a yellowish area on the side that is on the opposite side of what it was before. Before it was located here for barium sulfate, but for strontium sulfate, it's located down here. So you're actually moving further away from area of precipitation, but you are still above 1, so you still have some risk of seeing it. Now, top side, we have this point here we are starting at from the producer. You can see this yellow, it's slightly more yellowish than this side here. We have 1 here, so saturation is here, so you don't have any oversaturation at this point. But as you move, and that's when you move through the heat exchanger again with a straight line, so decreasing pressure, CO2 pressure and temperature equally or at a constant rate. And then you end up here, and that's where you inject. That's down here at a low temperature and low pressure. And then you move up of this line here, that's where you inject. So you end up here at the bottom. So you don't really have that much of a risk of strontium sulfate precipitation. The calcium carbonate looks like this. The producer, there is no one saturation index line, so you are below 1. I mean, you have a green risk, even though, as you are below 1. The same, no calcium carbonate scaling is assumed it's seen in the producer, and of course this is the major difference between this and the oil producer was that the oil producer was from a chalk field, whereas this is from sandstone, so you don't have the same amount of calcium carbonate supply. However, when you go to the top side and you see a decrease in temperature and you see a decrease in the CO2 partial pressure, you do see that there are parts of this regions shown here that have CO2 potential as a scale. And that's because the calcium carbonate and CO2 are very connected in terms of equilibrium and very sensitive to one another. So as long as you don't go into these areas, you should be fine. And then the injector starts down here, goes up here, and you see we are still below 1 and still in the all clear section or the green section. The last salt here is iron carbonate, and it looks a lot like the calcium carbonate. Is that you don't have any precipitation in the producer. You have, for the given production conditions, you have no precipitation. You do have some areas of that which can lead to precipitation. That's mainly due to loss of CO2 in the aqueous phase. So that's only this region down here. And then injector again, no precipitation seems possible because you are below 1 in the saturation index. So when we look at these 2 examples, we have the historical data and we have the risk-based for one sample here. And there are some pros and cons, of course, to what model would be best suited for the conditions that you have either in the oil well or the geothermal system. The pros of the historical data is that it can be more detailed because you have a lot more data in it. It can tell you the composition, and it can tell you where in the well you would have what kind of composition. and you would know what it was. You have a well profile, so it would be easy to say, okay, now we estimate that we would have a major calcium carbonate downhole, so we need to do a workover. Or we can see that with the treatments we're doing, we don't really have any scaling issues. And you also, of course, you can see the status of the well by this. Things you have to be aware of with this model is that it requires a lot of data. And of course, when it requires a lot of data, you have to be aware of the quality of those data. I mean, the model is only as good as the data. So if the data is bad, then you can end up with a wrong prediction. That's true for a lot of things, but just the more data you use, the more sure you have to be of those data. And of course, it's more complicated to understand because there's a lot more things going on in just one plot. So it takes time to actually understand what you can read from this plot. For the risk-based sample, we have that it's the pros for this one is that less data is needed. We only have that one sample that we actually need. It's a bit more intuitive, it's a bit more simplistic and easy to read. We have a wider range of production conditions. As you saw, we have a wider range of temperature and pressure. And you can have an easier time evaluating production changes. I can actually go back and show you that. Let me see here. So for this barium sulfate, for example, you have this, maybe you have this production conditions, but you actually don't want risk that much barium sulfate. So you decide instead that you want to start degassing first, and then you want to decrease the temperature afterwards. So you spend a lot more time in the green area and a lot less time in the red area. If you started up by decreasing the temperature and then degassed, then you would see a lot more, you would be in the red area for a lot longer and you would see potentially more scale. Just a quick side note there. So you would have an easier time to evaluate the risk by changing these production conditions. On things that you'd be aware of when using this kind of model is that it's less detailed in the way that you don't have that many information. It might be good or bad, but nonetheless you have less details. And you have to be aware that you only use one sample for these plots. So if you have sort of a sample that doesn't represent the condition, is somehow doesn't give the correct ion composition that is actually downhole, then you can have a plot that doesn't match your well, and then you are basing your decisions on wrong things. But overall, these are the pros and cons for both the historical data and the risk-based one that we looked at. And that's all for me for now. So thank you very much for your time.
Okay, thank you very much, Ida.